And we ran it over the summer. MIT said that it was working perfectly over here. The air conditioning was working up to spec. We turned our system on. We saved roughly about 25% energy, much less chilled air. So right away, we're saving energy. That's good. And people are more comfortable. Before we turned the system on, nobody was really comfortable in their office in that building. We turned it on, people are much more comfortable. Because again, it's regulating to their individual comfort, a model of their comfort, not to the temperature on a wall. So it's an intriguing possibility. More comfort, less energy, it's a win. And then, even more than that, we're looking now at lighting. Lighting is intriguing for a few reasons. You want to, of course, save energy. We all want to do that. And right now in our new building, we have motion sensors so that in the evening, if nobody is there, nobody is moving, it turns all the lights off. And that could be inconvenient because if you're working behind a lab bench, we have lots of lab benches in our space, the motion sensors don't see you. You have to go up and walk a couple of meters to turn them on. So the systems that we have now, certainly in terms of energy control, are much too coarse. But then look at the user interface. This is how we turn the lights on in our building. I have no idea how to work it. It's broken. User interfaces for lighting just aren't keeping up with the technology. I know how to turn the lights off, I think if I push this button on the bottom, but I have no idea how to do anything else. Never mind set the lighting so that part of the room is brighter than some other part. It's very, very cryptic. And it's ironic because the actuation possibility with lighting is getting better and better. With solid state lights or even the kinds of modern fluorescence like we have in our building, I can actuate any group of 3 or 4 lights separately through the network. So the control is really wonderful, but the user interface is broken. So how can we address this? What kind of leverage can we make of all the sensor data that we're creating to be able to make a better interface for lighting? So we're doing this a few ways. One way is to actually use sensors, and we've demonstrated this in our lab. Some of you have seen this demo, where we build little devices that can look at the amount of light that comes from each separate fixture. We can modulate fixtures by putting a modulation code on them. For solid-state lights, that's what happens anyway. We found ways actually of modulating fluorescent lights even with a passive device that can interfere with the plasma flow through the tube. And we can detect the specific amount of light coming from every fixture in the field of view on this sensor, and a linear program sets up to optimally give me the most energy efficient lighting at a given point with this device. So I just tell it how much lighting I want, put it there, it will give me the energy optimal light there according to what I desire. We have other systems we're building for lighting too, but I think it's an intriguing application because we need a solution. This technology can afford a good one, and it's an area that isn't really mined so heavily yet. It's really got tremendous promise. This is a device we're developing now. When you guys come for the sponsor meeting in April, you'll be able to see it. We call it the RISC key. So it's the universal key for this whole ubiquitous infrastructure. And I think it can't be a phone in your pocket because that's not seeing or hearing with you. It's buried. It's got to be out experiencing the environment you're experiencing. And the wrist works for very much of this. I mean, it works very well for temperature, humidity, controlling the air conditioning as we did in our past study. It can work for the lighting. We're going to put our lighting sensors on this as well. You can put your wrist out and adjust with a slider on your wrist to get the energy optimal lighting at the place where you are. We're putting an ultra-wideband radio on it. We're working with Qualcomm, one of our sponsors, who have developed a really nice low-cost chip for ultra-wideband radio that can give you centimeter-level positioning. So we know to within centimeters where you are, where your wrist is. And we're looking at different kinds of gestural control. So you can actually point with this. You can gesture in different ways. You can control displays, control interactive media, control lighting. Gesture control with lighting. I put that there, demo, using the old Media Lab vernacular for lighting. Is one of the things we want to do using this device. We've also put sensors onto athletes. This is actually a project we did with the Boston Red Sox that's continuing. It's in this last year now. My student is going to graduate. We've put several generations of sensors onto players. We basically measure their motion, their forces, their torques, things of that sort. We can infer directly the kind of parameters that really define whether they're going to be injured or not. Excuse me. We're going down to spring training. We're putting these sensors onto athletes actively now. I'll give you a little bit of this video since I have some time. This is taken at spring training about a year ago. So you can see, they didn't let us put the sensors on Dice K yet, but we have put them on minor league players that are going to be drafted into the team. That's one of our doctor collaborators. He's put the sensors on the wrist of a pitcher. And now we have straps that will Velcro onto the player. They're designed by an orthotist, so they fit very well to the body. Back then, we were putting 2 layers of tape. We put sensor on the chest. They usually do optical trackers, but it's very, very difficult to calibrate those systems and to make them work reliably in different light levels. And here we can just put the sensors within about 2 minutes onto a player anywhere in the batting cage, in the bullpen, and get data off the player immediately. And then we can begin to analyze it. So there's a batter. He's got sensors on the bat, on various parts of his body, on his arm. I'm holding the base station there. And then we put them on pitchers too. So we'll be going down to spring training again this year. This year we have a whole new generation of hardware that we're going to use to track players throughout the whole season and begin to try to mine it for performance indicators. There's a pitcher right at the edge of human capability. It's amazing what these guys can do. We see forces of 130 Gs, 120 Gs on the arm at peak. And we have a dossier for every player now with peak forces, peak torques. Now we're getting into joint angles because we have a compass. And we're again working with their doctors to mine this for factors that could be indicative of injury or performance. This is the last thing I'm going to talk about. It's gotten amazing press the last few months. We gave a paper at ACM Multimedia on it just a couple of months ago, and the press has gone totally wild with it. This is just a couple of the articles, but they're appearing everywhere. My student who did the voice for this little device was interviewed for Canadian Public Radio, so it's starting to take off, and it's an intriguing idea. It's thinking about, again, cameras going beyond just taking an image or taking video or finding somebody that's smiling or finding a face. You're engaging now in a dialogue with people. So you think of the camera as a robot. The robot basically is trying to coax a story out of people. You can let the robot loose in a place and it will build a story, build a structured narrative, a story about the place where you let it loose. So my student Alex Rebin built this thing, let it loose in the Media Lab, and it basically built a documentary about the lab. So here's Boxy. It's very cute. He built it to be cute so people would want to engage with it. And this is taken from the camera and the robot. So it moves around, and it gets stuck. Robots get stuck all the time. We leverage that. It asks for help.
Help. If you can help me, press the ring button on the side of my head. What is your name?
Aaron. Benjamin.
Agnes.
Santiago. Siggy.
Star.
Asa.
Adriana. Marina. Becky.
Dan.
My name is Henry.
Vincent.
Celine. Johnny.
Can you tell me what you do here?
I work in the academic program and I help students graduate. Mika's in HR. I don't know if you can see her. She's over here. Say hi, Mika.
Hi.
I run a research group called Software Agents, and we study common sense knowledge.
I find myself stranded right now because I was supposed to go to Munich today, but the volcano in Iceland kind of prevented that. Put a kibosh.
Can you take me somewhere?
So we asked people to
upstairs,
take the robot somewhere else so the robot can move to another part of the building.
I need coffee.
We asked them to show something you normally do there, so Santiago makes coffee. And then we try to push them and ask people to dance. And that's our academic coordinator. Now that this has gone viral, he'll probably never live this down. But again, we keep pushing people further and further to see how much they'll tell the robot. But because it's a structured dialogue, we have a structured set of videos that can automatically fit into a documentary. The robot also had an accelerometer on board. And it's intriguing looking at how people fell into two classes. People that completed the interaction were gentle. People that didn't complete the interaction were rough. They'd kick it, they would be rough with it. So you start to see the beginning of human-robot violence here. These people, saw it as a little animal, something cute. People here saw it as just an annoying piece of mechanical crap. So we're seeing a bit of the future right now. Okay, thank you.